Hey there, physical science students. This is Miss Ruark. We are in the motion chapter, chapter 11, and this is actually vodcast 2.4. I don't have it written on here, sorry. All right, so we're in vodcast 2.4. We're dealing with motion. We're still dealing with forces and all that. So let's jump in. All right, motion. What is motion? Motion is an object's change in position relative to a reference point. All right, so Mr. Rook, what's a reference point? Well, a reference point is an object that you can use to compare if you know where you're at from one place to where you're at in another place. So in this picture here, this lighthouse here is a reference point for the kayaker. So if the kayaker started up the river and did not see the lighthouse and then now sees lighthouse, he knows that he's moving. Also, if the kayaker starts over here on this side of the picture and then goes around and ends up on this side of the picture, well, the lighthouse has changed position, which means that actually the lighthouse hasn't moved, the kayaker has moved. So it's a point of reference for someone to determine how far they have traveled. All right, displacement versus distance. We've talked about this at the beginning of the year, so we're going to do a little quick review of it. Distance is how far an object has traveled along a path. Okay, remember, distance is how far the object has traveled. It is the total, and I don't have this on here, but it is on your notes. It is the total distance traveled, or total, well, I don't like that. Total length traveled. Let's put it that way. Total length traveled. I think that's what it says on your notes. Okay, so the total length measured in whatever unit is you decide to measure it in, traveled. All right, well, displacement, what is displacement? It is the shortest distance between start and finish. It's the shortest path between start and finish. Okay, displacement must include direction. And so remember, when we talked about this at the beginning of the year, when we talked about scalar and vector, scalar is something that always has just a magnitude. It's a number and a unit. Okay, and then displacement or a vector is going to be something with direction. So displacement, write this on your paper if you don't remember, is a vector, and distance would be a scalar measurement. Okay, write those things down. That's important. All right, so for example, the distance that was traveled by this cross-country runner, remember we use this in class, the distance traveled by this cross-country runner, the total length that was covered by this cross-country runner with all of the twists, turns, ups and downs in it was a total of 3.1 miles. Okay, but the displacement from start to finish, the shortest path, straightest path from A to B, the displacement here could be just 1 mile. Okay, so displacement is not always the same as distance. All right, speed and velocity. Here's two more. We talked about these when we talked about scalar and vector. One of them has just a magnitude and a unit, and the other one has magnitude, unit, and a direction. All right, well, speed is how fast an object moves. It's how fast it moves per time, so it's a rate. Okay, so the example for this is miles per hour. So here's our car over here, right? Miles per hour. We also see kilometers per hour. Okay, those are ones that you're familiar with. Okay, we in this class will be using meters per second because we like to use the metric system. Remember, this is the English system, this is the metric system. We go with the metric all the time. Anytime you got meters, that's a good thing. All right, velocity is how fast an object moves, and it tells us what direction it's moving in. Okay, so speed is going to be a scalar measurement, S and S, and velocity is a vector measurement. Okay, and if you guys don't remember, and I say it in class all the time, vector commits crimes with both magnitude and direction, and that's how you can remember vector versus scalar. Okay, also velocity, because it's a movement and it's a direction with it, it uses a reference point to show which direction and how far it's been moved. Okay, velocity can actually have a positive or a negative velocity depending on which direction it's moving. So an object moving in one direction along a line of motion would be a positive velocity, and an object moving in the opposite direction along a line of motion would have a negative velocity. Okay, well, what does that mean? Well, let's say that this is our line of motion here. Okay, let's say that this is where we started at. This is our house. Okay, and here's our house. See, I'm going to draw you a house. There we go. All right, and here's the smoke. Okay, so here's our house, and we're starting at our house, and we've got to go to the store. Okay, so to go to the store, we're going to go, let's say 2 miles in the positive direction. All right, well, to go from the store back to our house, we have to go a negative 2 miles because we're going in the opposite direction if we go this way. All right. Okay, resultant velocity. Resultant velocity is when you take the sum of all the velocities. So you take them and you add them all up together. All right, well, here's an example, or 2 different examples of ways that they can add up. On this one here, we have, on this first one here, this one here, okay, we've got the plane that's going in one direction of 100 kilometers per hour. Well, the wind is also blowing in the same direction as the plane at 25 miles or kilometers per hour. So we add these two together and you have a resultant velocity of 125 kilometers per hour. Okay. Have you ever been out when you're walking and it's one of those really blustery, windy days in the winter and the wind is just blowing crazy? Okay. Usually this happens like around February, maybe March, and it's just blowing like crazy. And you start walking and it's blowing behind you and you feel like it's like pushing you. Okay. Well, here it's because your resultant velocity is however fast you're walking plus the speed of the wind. All right. Well, this one here, we have the same plane going in this direction at 100 kilometers per hour. But guess what? The wind is blowing against it at 25 kilometers per hour. And you know what this feels like because you're outside walking and all of a sudden that gust of wind comes and it blows and you feel like you're not going anywhere. You're just walking in place. At least that's what it feels like. Okay, and it's because the wind is working against you. So it actually subtracts from your velocity and your resultant will be less, so it's 75 kilometers per hour, which is less than what you originally started out at. All right, when you calculate speed, speed is the distance traveled over a specific amount of time. Okay, so it's distance over time. All right, so the SI unit, or the known or accepted unit for speed, is meters per second, or m over s. Okay, little m over little s. And the average speed, if you were to find the average speed, is the distance traveled by an object and the total time the object takes to travel that distance. So, if you were to get on the interstate and drive to Atlanta, okay, and while you're going there, you cover so many miles, whatever the distance is between here and Atlanta, let's say 120 miles, 130 miles. Okay, you cover 120 miles in 2 hours. Right, so if you were to convert all that to meters per second, you would be able to get that. You could do it in miles per hour as well, right? So 120, if we were to do that in miles per hour, we would have 120 miles divided by 2 hours. And that ends up giving us 60 miles per hour. And it says that on average, you traveled 60 miles per hour. That was your rate. Okay, it's just speed because it does not have a direction. So that gives us our average speed. Okay, it does not give us instantaneous speed. We can figure that out by looking at the speedometer, because at one point you could be going 70 miles per hour and then later you get stuck in traffic and you're going 30 miles per hour. So the instantaneous speed would be different from your average speed. Okay, so to calculate your speed, velocity and speed are actually both the same thing. It's going to be distance over time. Distance over time. Okay, just remember that velocity, you're just saying what direction as well. All right, so here's an example problem. Here's our little sledder who's sledding down a hill. And if this sledder has moved 132 meters in 18 seconds, what is her average speed? Okay, so how do we do this? Well, remember we plug in distance over time. So we put 132 over 18 and we just simply divide. So if 132 divided by 18 gives us 7.3 meters per second. Now the meters and the seconds do not cancel. The only way they'd cancel is if it was the same. So your answer remains with units of meters per second, just like that. All right, and then instantaneous speed, I told you earlier, was the speed of the object at any given time. So this would be the average speed of the sledder. You could calculate, you could find the instantaneous speed by, using a radar gun or whatever. Okay, moving on. Okay, let's do another example. Let's say this right here. Here's a big old glacier, and this is actually a picture of the Black Rapids Glacier up in Alaska, and it says metal stakes are sometimes placed in a glacier to help measure the glacier's movement. For several days in 1936, Alaska's Black Rapids surged as swiftly as 89 meters per day down the valley. Okay, and they want to know the glacier's velocity in meters per second, and you have to include direction. Well, here's an issue because this is meters per day, so you've got to change from days into seconds. You got to go from days to seconds. Okay, so we set this up. We know that we have 89 meters, but we don't know the time. We've got to get from days to seconds. So to find the seconds, we know that in one day there's 24 hours, and we know that if we multiply by 1 hour over 60 minutes over 1 hour, right? So hours cancel, and because there's 60 minutes in 1 hour, we're left with minutes. We still got to get to seconds. So we cancel out our minutes by putting 1 minute on the bottom and 60 seconds on top. And now we're left with a unit of S, which is our seconds. And so now we have how many seconds it takes to travel 89 meters. So we plug that into the bottom of that top equation there, and we solve for 0.0010 meters per second down the valley because we have to tell the direction. We're going to practice these in class, so don't freak out if you're like, I don't know what I'm doing. It's okay, you will. All right, graphing motion. Oh, it's hard to see the axes. Sorry about that, or the grid lines. These are the grid lines right here. Okay, so if we wanted to graph this data table right here and put this in, we would put time on the x-axis. We always put time on the x-axis, always. And we would always put distance on the y-axis. Okay, so distance on the y, time on the x, always. Never any doubt on that one. All right, so when we plug this in and we draw lines to connect the dots for all of these, we end up with a graph that looks like this. Okay, remember that your x-axis is going to be time, and that's where your independent variable goes. Your y-axis will be distance, and that's your dependent variable. Okay, and then your slope here, if you notice that your slope, because your slope is equal to rise over run, right? So the rise is distance over the run, which is time, and that gives you velocity or your speed. So your slope of a motion graph will always be the speed that you're moving. All right, so if it's a slow-moving car, if something is moving slowly, you're going to have a very slow incline on your slope. It's going to come up really gradually, very gradually. Okay? If you have a fast-moving car, your slope's going to be a little bit more dramatic. It's going to go up. And if you have a super fast car, it'll go up like that. Okay? It should be really fast-moving. Your slope will increase more and more as you go. If the car is changing speed, you'll notice that your slope will vary. Okay, here it was moving at a continuous rate, and then it slowed down a little. And here it just kind of flattened out. Well, here it flattened out, right? So here we're sitting still. So maybe it's at a stoplight, and then it starts to increase again. So it's left the stoplight and it's going forward, and then it's picking up its pace again. Okay, so the car right there is at rest. How do you know? Because if you look, the distance isn't changing any. It's staying the same. It's flat. Okay, if the distance was going up, then we could say it traveled. But since it's not going anywhere. All right, and that's it. We're going to practice more of this in class, and I'll see you in class.